Here are 6 different problems about prime numbers, some of which are doable and some of which are so incredibly difficult that they are open problems in mathematics, in number theory, and you would be famous if you were able to solve one of these. Can you tell which ones are doable and which ones are open problems in number theory? The problems are find all the prime numbers p of a given form. So for example, this one is find all the prime numbers p that are 1 less than a square. In here you have to find all the prime numbers p that are 1 more than a square, etc. So pause the video here if you want to try it out, because I'm going to give the solution. So here is the solution. Doable, 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 open problem, open problem. For the numbers that are 1 less than a square, this can be factored as follows, and therefore, since this product is prime, one of the two factors has to be 1. This is a smaller one. This is 1, so n is 2, so p has to be 3. If 1 less than a square is the square of a prime, I can move the p squared to this side and the 1 to that side, and I get that n squared minus p squared is 1, and therefore I have this factorization has to be 1, and the only possibility is that this is 1 and this is 1, so n is 1 and p is 0, which is not prime, so there are no such primes. Similarly, if 1 more than a square is a prime squared, I can move the n squared to the other side, factor it, and then this has to be 1 times 1, so p is 1 and n is 0, but p equals 1 is not a prime, so there are no such primes. If 1 less than a square is twice the square of a prime, then you see this product has to be even, but if this is even, n plus 1 is even, and n minus 1 is even, and therefore p itself has to be 2, and if p is 2, p2 actually works because 8 is 9 minus 1, so there is only one such prime, p is 2. Now, if your prime is 1 more than a square, we have no idea if there are infinitely many such primes. We think so. For example, 2, 5, 17, 37 are such primes. And Hardy and Littlewood have conjectured that there are infinitely many of them, and in fact give you even some formula for an approximation to expect how many such primes are there up to x. So if you were able to solve this, you would be famous because you would probably solve the Hardy-Littlewood conjecture. Now, if your prime is such that 1 plus a square is twice the square of a prime, then if you start doing computations, you find that 5, 29, 5,741, 33,461 are such primes. And then I put my computer to run and I tried the first million primes and I couldn't find any other solution. So you might wonder, like, is this it? Well, if you keep going, then there are more primes, such as that huge prime or that gigantic prime is a solution. And the reason for that is that such primes correspond to what we call coefficients of a Pell equation, and there are methods on how to find solutions to this. So the question is whether there are coefficients of Pell equations that are primes, and we believe there are infinitely many such points on a Pell equation that have prime coefficients, but we don't know that. So again, whether there are infinitely many such primes depends on that conjecture, which we have no idea if it's true or not.